Hello and welcome. In this video we are going to analyze functions of three variables. So to motivate this, we often have a dependent variable, and to date we've only considered multivariable functions that have an output based upon two inputs, x and y. And we call this a multivariate function. We've been able to say that z is a function of x and y. So now we can model dependent variables that rely on two inputs. So maybe z represents the price of a gallon gas, the cost to fill up your tank, and x represents the number of gallons that you get, and y represents the cost of a barrel of oil. So it's not uncommon that we have outputs that depend on multiple inputs. But now suppose that instead we're going to have x, y, and z, so potentially three inputs that affect some output, which I'll just refer to here as f of x, y, z. So we could say something like w equals f of x, comma y, comma z. So in this case, we're able to use three inputs as a predictor for our output. Now that poses a little bit of a visualization problem. Specifically, in order to have four variables in x, y, z, and the output based upon those three inputs, we would have to have four dimensions. So let's start off by defining something that will help us make this problem a little bit more manageable. So a level surface, or level set of a function of three variables, f of x, y, z, is a surface, so surface just means three-dimensional function, of the form f of x, y, z equals c, where c is a constant. In translation, what we're doing here is we're saying, okay, well, if we can't see it in four dimensions, let's hold the output value fixed, almost like we were looking at a contour plot, and for that fixed value of c, we're going to get a relationship between x, y, and z, meaning we're going to end up with a three-dimensional function by holding the fourth variable constant. So it's nothing really super new here, except that our representation will not be a 2D representation of a 3D function, but a 3D representation of a 4D function. The function f can be represented by the family of level surfaces obtained by allowing c to vary. So we get what's called a family of level surfaces when we consider all of the different possibilities of c. Let's take a look at a practical example. Suppose a company sells three types of parts, one for $4.99, another for $5.99, and their elite model for $8.99. Let x, y, and z represent the quantity sold of each of these three parts respectively, and so x represents the numbers of the $4.99 part sold, y the $5.99 part sold, and z represents the number of $8.99 parts sold. And let r be a function of x, y, and z, and that's going to represent the total revenue collected from sales. So that just means how much are they going to have, how much are they going to bring into the business at the end of the day. So revenue is calculated by taking, well, how many parts do you have at $4.99 per part multiplied by the price? So that will just give me the total revenue generated from part one. $5.99y will give me the revenue just generated from selling y quantities of part two, and $8.99z will represent the revenue associated with selling z units of part 3. So how do we begin analyzing this? We've already mentioned that we would need to add a fourth dimension, but it's not easy to visualize four dimensions. So here's that idea, this level surface idea is getting at. If we hold the value of f of x, y, z constant and look at its resulting three-dimensional reductions, we can see how it operates. In other words, any fixed revenue will show us all the combinations of x, y, and z that achieve this revenue. So we can take a look at a 3D plot of this and be able to vary the values of the revenues. Here I just have three of those plotted already. This is when I've set r equal to 10. So what that translates to is we're essentially saying 10 equals 499x plus 599y plus 899z. This is a linear function, and if we solve for z in this linear function, we could express it in the what we would usually refer to as the slope-intercept form of an equation. Here we would have the same thing, but it would be 20 equals, and then this right-hand side, and here it would be 30 equals. So we've successfully removed one of the variables by holding it constant. What happens here is when r is equal to 10, and this is just the first quadrant that we're looking into here, or the first octant, because we had 8 of these regions, 4 above the xy plane and 4 below. And so we see just really, in terms of practical values, just this portion of points along the plane here generate realistic combinations of x, y, and z. So any point in this little region, in this little triangle, so you can see that those 3 points right there represent the intersection. So that little triangle right there of points represents realistic combinations of the 3 parts, the quantities of those 3 parts that will generate a revenue of $10. Now when we make that revenue bigger, of course, now our maximum number, so here you can see that it's about 4 on this axis, and I'm going to guess that to get 20, 4 times $4.99 is approximately $20. So I'd say this is the x, the y, and the z. Alternatively, we could sell 1, 2, 3, about 3.5 of the y parts, not quite 4, because 4 parts would put us at about $24 of revenue. And same thing right up here, we could do a little bit more than 2. It's kind of hard to see where that intersection is, but you can see that our triangle grows a little bit, and now the possible combinations of quantities for these 3 parts has expanded. Now anything in between here will work as well. Any one of these points inside of this triangle on this plane will represent realistic values. Of course, you could pick something over here, but that would give you a negative value of y, and of course we can't sell negative parts. And if we now look at revenues of $30, of course, well, that means we can have nearly about 6 of this first part, and about 5 of the second part, and about 3, a little over 3 of the third part. And again, you can see that this triangle just gets a little bit bigger, our window of possibilities. Any point in here will also generate that revenue of $30. So our conclusion would be that each level surface for r equals c, so some fixed value of revenue, represents a plane of possible parts, a plane of possible part quantities, resulting in a revenue of C dollars. Let's go ahead and jump over to this website, which will allow us to take a look more closely at these graphs. So here we have GeoGebra 3D pulled up, and we can begin by just taking a look at the revenue of $10. So I'll type in 10 equals 4.99x plus 5.99y plus 8.99z. And you can see there's that plane, and we can rotate this by just clicking and dragging, and you can see this a little bit better that, of course, this is our positive x, positive y, positive z. So there's that little triangle for the $10 revenue. Now, one little thing that I'm going to do here is I don't want to have to keep changing this 10, so I am just going to say r equals 0. And all that will do is that we'll just insert a slider, because r is not a recognized value. So by default, this software will insert a slider. Right now that slider doesn't do anything other than just display the current value. Now, since this is our revenue, we can come in here into settings, and we can click on the slider tab, and we can set our min value for that slider. So of course I don't want to see negative revenues, and we'll go ahead and drag this up to 30 just for demonstration purposes. Now you can see our slider goes from 0 to 30. So we can close this window, and up here in this equation, now instead of plugging in 10, I will replace that with capital R. And so all that will do is now you can see that right now the equation is equal to 0. You kind of have to ignore this. It rearranges some of the values in that equation, but this is still equal to 499x plus 599y plus 899z equals 0. In fact, if you divide by -1 on both sides, you get exactly that equation. So as we begin to shift this slider value, we can start to see exactly what we saw before. That triangle of possible values grows as we increase the value of r. Now, on first look, it kind of looks like the plane is just wobbling, but if you look at it from a different angle, a more of a two-dimensional perspective, then you can see that really all we're doing is shifting that up and down. We're creating a shift of this plane. So, of course, what that means consequently is that as I make R bigger, the possible values for X, Y, and Z also become bigger because now I'm asking for a bigger revenue, so I have to sell a greater number of parts. We can also take a look at it from other perspectives. Again, it kind of looks like it's maybe moving backward and forward, but when you do see the 2D perspective, we can see that it's a vertical shift. So there is much value in doing this. One, if I were an analyst for this company, I could conclude that these different graphs just simply show us the set of all possible values of quantities of parts that would allow me to achieve a desired revenue. So it seems kind of backwards because usually you know how many parts you sell and you want to determine the revenue, but maybe I want to see, okay, what would I have to sell in order to make a certain revenue of, say, $10 or $20 or $30 or $1,000. So we have no limit on what we can place on R, but the family of curves, the family of level surfaces, this is a level surface, this is a level surface, this is a level surface of our four-dimensional function, and the collection of all of them, so there are obviously infinitely many because revenues could be between 10 and 20, and there are infinitely many possibilities for that revenue. Of course, maybe you can't sell fractional parts, but mathematically speaking, the family is the collection of all of them for all values of R equals C. Let's take a look at another example. A large industrial oven is used to sterilize surgical tools before they are packaged and shipped to hospitals. The oven is a rectangular prism that is 16 feet by 12 feet by 10 feet, length by width by height. So probably what we want to visualize here is we have this rectangular prism. I'll try to draw a rectangular prism. Here we go. There's our rectangular prism. And so, or there's our base of our rectangular prism. So we have something that looks like this. And I'll just draw a dotted line there. And we're going to get something that looks somewhat like this. There we go. Okay, so we have this rectangular prism inside of this. This is 16 feet by 12 feet by 10 feet. Due to the size of the oven and the location of the heating element, temperatures can be wildly different across different points in the oven. If we let X, Y, and Z be the distance in feet, in the length, width, height direction. So X represents how far, say, to the right or left you are of this particular point, 0, 0, 0. Y represents the distance backward or forward, and Z represents the distance upward or downward relative to this point, 0, 0, 0. Then the temperature, T, in degrees Celsius is given by T of X, comma, Y, comma, Z equals 200 minus X squared minus Y squared minus Z squared. So first of all, we want to know where is the heating element located. So before we start visualizing this, let's just conduct a little algebraic analysis of this equation. So where the heating element is located, we can assume that this is the hottest point. It's not always trivial to analyze these types of equations, but I see that what's going on here, or one other way that I could write this, is as 200 minus the quantity x squared plus y squared plus z squared. And what that allows me to see is that if x, y, and z become anything bigger than 0, then we're taking the temperature, 200, and we're subtracting something off. So when x and y and z are all equal to 0, we see that we get a temperature of 200 degrees Celsius. Now, making these negative won't work either because, well, if we make any of these negative, they get squared and we're still going to be subtracting off positive values. So 0, 0, 0 is located here in the center. So we'll just say this is the rough center. So that's the center length and width wise, and then here's the center of that room. So we have this heating element sort of suspended there in the middle of air. So we can say that the hottest point, or where the heating is located, is at the point x, y, z equals 0, 0, 0. And our argument is just that the reason it's the hottest is because if you make x and y anything other than 0 and z, then you're going to be reducing the temperature. And so the temperature at 0, 0, 0 is going to be 200 degrees Celsius. So it's a very, very hot heating element. All right, let's go ahead and take a look at the graph of this surface, or let's take a look at the level surfaces of this family of level surfaces. So here's our applet designed specifically for this problem, and we can see that if we want to vary the temperature, what we're going to do is we are going to, this is just one form of that equation. Notice that this is the same thing as x squared plus y squared, it is 200 minus x squared minus y squared minus z squared. Now, as I change the temperature, let's just take a look at the shape. So first of all, if you rewrite this and you isolate x, y, and z, you have x squared plus y squared plus z squared. And I'll talk momentarily about why we wrote it as 14.14 squared. But if you square 14.14, you get about 200. Okay, so as I begin changing this temperature, let's see what happens. So it's a sphere, and as I make this temperature, let's say 180 degrees, I have a very small sphere. Well, what is the meaning of having a very small sphere? The meaning of having this very small sphere is that x, y, and z all represent, they represent the positions within the room, how far away from the center. So imagine that this origin represents the center back here in our rectangular prism. So all the locations are all the coordinates in the room that create a temperature, in this case of 180 degrees Celsius, are all the points surrounding this sphere. So one of the things that we can imagine is that that heat radiates in a radius, and the farther you get away, the temperature is going to drop. So if I want to figure out all the points where the temperature is going to be about 100, let's see if I can get it. I can't quite get it to 100, but close enough. So all the points on this sphere right now represent all the locations in the room, assuming that these are still locations in the room and not outside the rectangular prism. These are all the points where the temperature is going to be 100 degrees. The reason we wrote it like this is because if we recall from our algebraic experience, if you write an equation of the form x squared plus y squared equals r squared, then the two-dimensional representations would be circles with radius 9.96. So if you're in the center of the room, or if the heating element is in the center of the room, you can go out to locations 9.96 feet away from that heating element and find a temperature of 100.8 degrees Celsius. If I want to find lower temperatures from that, it's too hot, that's boiling. So if I want to be closer to a temperature of freezing, which maybe that doesn't make sense in the context of the problem, we'll just say 23.4 degrees Celsius, then that's going to be the collection of all points that are located 13.29 feet away from the oven, from the heating element source. So with that said, we can think about this as the collection of all spheres. And we'll look at a catalog of surfaces here shortly to say, well, how do we know what kind of shape it's going to have? And really the short answer is there are a lot of surfaces out there. We're just going to look at some of the common ones. So it's unreasonable to expect that you can always visualize what one of those level surfaces looks like for that family. To remain sterile, tools must remain above 100 degrees Celsius at all times while in the oven. Does this oven guarantee that this will be true for all locations? Well, one thing that we could do is we could look at the extremal points of the farthest distances from that center. So let's approach it this way and say, we want to analyze the distance from the oven to the farthest reaches, which would be any one of these corners, and we can probably just intuitively even agree on that, or here, or to down here, or over here, or to this point. These are all going to be the same distance from that center. So if I pick any one of these points, let's pick on, say, this guy here. So that point, at least in the x direction, is located at -8 feet. So it's 8 feet to the left of the center. And then furthermore, it's located 6 units back, because this is centered at a distance of 6 along this axis, so that will be a value of -6. And furthermore, the height of this point is going to be, well, this is located 5 feet above the floor, and so we need to go down 5 feet to locate this point, so that will be at a point of -8, -6, -5. So we're going to look at extreme points, and notice that it wouldn't matter if we picked 8, 6, 5, which would be this point here, or we picked 8, 6, -5, or -8, 6, -5, because we're going to be squaring these values. So there's further justification for why it doesn't matter which point we pick. Okay, so let's check the temperature at this point. So the temperature at, and then we're saying we're going to use -8, -6, -5. So the temperature at position -8, -6, -5 will be 200 minus the x squared, which is 64, minus the y squared, which will be 36, minus the z squared, which will be 25, and that comes out to 75 degrees Celsius. So the answer is no. In fact, we see that there is a location that has a lower temperature. And we just did that logically by realizing that the farther we get away, the lower that temperature will be. Now, another way we could do this is we could say, all right, well, I want to look at the distance for temps of 100. And what I mean by this is that if we take our equation, 200 minus x squared minus y squared minus z squared, and we set this equal to 100, then now we're looking at the level surface where f of x, y, z is set equal to 100. So back in this picture, what we're essentially looking at is where the slider value is exactly 100. Okay, so this is 100.8. I can't quite get the slider there, but that would result, if we rearrange the equation, in x squared plus y squared plus z squared equals 100, which is, that's not quite 10 for the reason that I can't get that slider quite right, but this becomes x squared plus y squared plus z squared equals 100, which is the square of 10. So this means that anywhere farther than 10 feet from the element, the temps drop below 100 degrees Celsius. And now we can say, well, are there any points in the rectangular prism that are more than 10 feet away? And so we could calculate the distances to the corners and see that those are farther than 10 feet from the heating element source. So all of these different surfaces that we're looking at have some two-dimensional analogy. So we've seen parabolas in 2 dimensions. They're called paraboloids in 3 dimensions. And moreover, we can actually change that opening from being circular to being elliptical, and you can play around with these values of a and b, but if you divide x squared and y squared by some value, that's going to change potentially a circular contour to more of an elliptical contour. And we're not going to get into these surfaces themselves, but this is just kind of a catalog of different ones. Then you have a hyperbolic one, which notice just has a negative in front of one of the two variables. So this would be what we would think of as a hyperbola in a maybe college algebra type class. An ellipsoid, so it has the x squared plus y squared plus z squared form, but dividing those will give more of an elliptical feature. A hyperboloid of two sheets, a cone, a plane, which we've seen already, cylindrical surfaces, and parabolic surfaces, where notice here we're just missing the z value, so you have a bunch of parabolas that are exactly the same for all values of z. So let's take a look at the family of level surfaces representing f of x, y, z equals x squared plus y squared. We can begin by just taking a look at x squared plus y squared. Now, if we know that this is a three-dimensional function, but we're going to set it equal to some sort of numerical value. So if I set this equal to 1, for example, well, it looks like what I'm getting is a cylinder, and that makes sense because x squared plus y squared equals 1 just means that for every single value of z, notice that z is not in this equation, but if I put plus 0z, you'll notice that does not change the shape of the graph at all. So there is a z in the equation, it's just has a coefficient of 0, so its value does not affect the shape of the graph at all. If you look at this from the top, you can see circular cross sections. So our contours. You see circular contours going all the way down with exactly the same radius. Now if we change this 1 to 2, and in order to do that, I'm just going to go ahead and create a new value. Maybe I'll just call it a equals 0. And so then what I'll do is I'll just replace this 1 with a. This way I can control the slider. Okay. Now when a equals 0, you're essentially saying, well, that's going to be a circular contour with a radius of 0. But as I proceed to increase that value of a from 0 to 1.5 to 2 to 4, you can see that these are just going to be the same cylinders with different radii. This one, notice, has a radius of 2. Since normally when we write x squared plus y squared equals a constant, we like to write it as the square of some constant because the square root of a represents the radius of that circle. And you can see that I can continue to make it bigger, make it really, really small. Now negatives aren't going to make much sense. It's going to be an undefined equation, but we see that the family of level surfaces is the set of all cylinders with a radius, the square root of f of x, y, z. Now, why I say that is because a represents f of x, y, z, and the square root of that value gives me the circle. So, it gives me the radius of the circle. So the family of level surfaces is the set of all of those cylinders, and so we can write the set of all cylinders, and we should probably be more specific, all vertical cylinders with radius, the square root of whatever we plug in for f of x, y, z. So let's write it like this. Fix f of x, y, z to be some constant, and whatever constant you plug in right over here, replace that with the constant, the radius will be the square root of that number. So here we have f of x, y, z is set equal to 100, but you can see that that has a radius of only 10. F of x, y, z equals 10, more of a radius of about 3 point something, and f of x, y, z equals 1. Square root of 1 is 1, so that's a cylinder of radius 1. We can also see different types of cylinders. And the reason I had mentioned that is because if we simply change x squared plus y squared to be x squared plus z squared, it's still a cylinder, but now the cylinder is on its side. And the way we can think about that is this here is our z-axis, this is our x-axis, And in a two-dimensional world, x squared plus z squared is simply a circle of radius square root of a, but wrapped around the y-axis. The y-axis is the one coming out at us, so it traverses through the x and z axes, but runs equally along all values of y. And so again, I can put a 0 y here, and you see that's not going to change the shape of the graph, because for all y, for any value of y that I choose now, my cross-section of this graph will be a circle of radius square root a. And similarly, I could do something like y squared plus z squared, and so intuitively what that should be is a cylinder that is wrapped around the x-axis and that runs, cuts into the y and z axes. And you can see that that's true, and again we have that same cylinder, and I can change its radius by experimenting with it. Again, negative values don't do anything. 0 gives us a straight line, and if you see this equation here, z equals y is the solution, or for a equals 0, we would actually have an undefined value because z would have to equal plus or minus the square root of negative y, and the only value of y where that will work is going to be 0. Let's take a look at one more. How about something that is not in our library? And this is going to happen quite often in the real world, where we're not going to be adhering to these very well-known models because, of course, our functions are determined by the discipline and the types of analysis that we're doing. So if we take a look at this guy, I'm going to go ahead and summarize this first. We get these almost bowl-like shapes, and when f of x, y, z equals 1, when we replace that with a 1, we get these shapes, this almost hyperboloid of two sheets. It's not quite a hyperboloid, but very similar. When f of x, y, z equals 10, that's the purple surfaces. So notice that those foci kind of move outward further, and when f of x, y, z equals 100, they move out even further than that. So we can model this, and we can say x squared minus z squared plus 2xy equals a. And so now I can play around with this value. Now, unfortunately, it's some of these graphing utilities struggle quite a bit with using these more complex functions. So you might notice you might have some trouble rotating these the way you want it. It takes a lot of rendering power on the computer to do this, but you can kind of see that effect of these two sheets sort of move out further from one another. And then for even some negative values, you get something interesting going on here, and you can see that those actually connect. So the family of surfaces here is going to be the collection of all of these different graphs. You can see it looks like a couple of funnels put together. It's going to be the collection of all of these shaped graphs, and the type of surface that you get really does depend on whether you're using positive or negative values of a. So here you can see that they're bowls, they do not have openings in the ends, but when a is negative, you can see that the two bowls are now connected with an opening right through the center. So this is how we begin analyzing four-dimensional functions. The key idea here is that when we have a four-dimensional function, we analyze the family of level surfaces. And the family of level surfaces is just the collection of all the graphs that you could get for every single possible value of holding that output constant.